Good afternoon, Internet. I am Matt Buyak, and in this video we'll be taking another brief look at yesterday's problem, problem number 59 from the Project Euler Problem Archive. Now, this problem gives us an encrypted message and asks us to break the code, which I did successfully in yesterday's video. But to be honest, I kind of have mixed feelings about that video. Going into it, I knew that I didn't want to know the encryption key or the decrypted message ahead of time. I thought that would skew my approach. And also, cryptanalysis isn't the kind of field where there's one solution that always works. Sometimes you have to try multiple approaches before you have success. And I wanted to show that in the video. The downside is that it's rather lengthy. It's over an hour long. There's a period of time in the middle, 10 or 15 minutes, where I'm trying this technique that is just not working. But there are also some really great moments in the video. There's this point near the end where I'm just reading over page after page of partially decrypted message. And I have this epiphany where I realize, wait a minute, I think I can read this. Like, I can put together pieces of this word over there and pieces of that word over there, and I think I can guess what the first sentence of the message is. And if I can do that, I can reverse engineer what the decryption key is, and then use the rest of the message to verify that the key is correct. And when you see that decrypted message pop up on the screen the first time, it kind of seems like magic. It also kind of seems like cheating a little bit. And so in this video, I wanted to show the next approach that I would have taken if the technique that got me close enough yesterday hadn't been good enough. So let's get into it. We'll go back to our problem directory and open our main.cpp. Now, the general approach that we used yesterday, which is also the general approach that we will use today, is to just try each of the 17,000 or so possible decryption keys, try decrypting the message, and then score it based on how much it looks like an English message. Obviously, to humans, or native speakers of English at least, if you look at an English message, it's very easy to tell that it's decrypted. But for a computer, it's not so obvious. And so we have to come up with some scoring function to decide how much our decrypted message looks like a real message. And yesterday, we based our approach on frequency analysis. That is, we know it's posted on Wikipedia, what the most common letters are in the English language and the approximate frequencies at which those letters occur. And so our scoring function was basically just to give a decrypted message more points, the more characters it had appearing frequently in its message that also appear frequently in English. And actually, let's just take a quick look at the result of that. So you can, for those of you, I imagine it's most of you who didn't watch all the way through to the end of yesterday's video, you can get an idea of where we were at the point when we sort of made a leap and ended up with the solution. So if we go down here, go back to our shell, we can build and run. And this is going to print out the top 1,000 candidates. Probably a little bit overkill, but going up to the top, we can see that this is not an English message. And maybe if you kind of squint at it right and compare across multiple lines, you get kind of a sense for what the first sentence might be. And that's the approach that I took yesterday. But today I want to do something a little bit more sophisticated, perhaps. And the way we're going to do that, actually, is to borrow a file from an earlier problem. It's going to be problem 42. We have this file words.h. Let's open that up. And as you might guess, it is in fact English words. And so rather than judging our message by how many letters are appearing in different frequencies, we can just look at whether there are actual English words in our message. Now, this is more expensive than counting letters because there are so many, there are only 26 letters, but there are many, many English words. So we may have to let our program sit for a moment in order to actually come up with the answer, but we'll see. So first, let's switch this over to being a set. The main thing we want to be able to do is check to see if a candidate word is in this set. And that's going to be much faster with a set than with a vector or some other random access container. Okay, so let's go back to our scoring function. There it is. And we are not going to use this scoring function. We are going to write our own new scoring function. Okay, taking the same argument, just a string. Okay, so we want to scan over our string for bits of the message that look like an English word. That is, they're all either lowercase or uppercase characters. And if they're lowercase characters, we'll want to convert them to uppercase characters since all the words in our words.h are in uppercase. Okay, so let's say for char ch in str. And we're going to want to have a string which contains the word that we're building. So we'll say std string word. And we'll want to start by saying ch equals to upper ch. Note that if ch is not a lowercase character, this call will have no effect. It just returns the same character that you gave it. Okay, and then we want to say if is upper, that is, if it is in fact an uppercase character, then we want to add it to our word. So we'll say word.push back ch. If, on the other hand, it is not an uppercase character, that breaks our current word, and so we'll want to check the word that we just built to see if it's in our set. But we do need to check that the word is non-empty. If we're right at the beginning of our message, or if we have multiple garbage characters in a row, then the string might be empty. So we'll say else if not word.empty. Then we'll say if words.find word is not equal to words.end. So the way this find function works is that if it fails to find your word, it returns an iterator to the end of the container. And so we just say if it's not equal to words.end, that means we did in fact find the word in our set, and so we should increment a counter to indicate that we found a word. Okay, so after we've scanned over our message, we have to be sure to handle any characters that form a word at the end of the message. That is, if we have a word in progress, we won't have checked that yet. So let's say if not word.empty. Oh, And there's actually something rather important I've just realized that I forgot, is after we check that our word is in fact a word, we need to do word.clear so that we can fill it with the next word. Okay, now if word is not empty, we do the same thing. We'll say if words.find word is not equal to words.end plus plus count. Okay. And then we can just say return count. And let's see how this new scoring function works. Rather than printing out the top 1,000, let's just print out the top 10. And actually below that, let's print out the full message for the top 1. So we'll say printf, we'll just say %s. And that's going to be candidates 0 second C-stir. And we don't need any of this nonsense down here. This was just part of our guess from yesterday. Okay, back to the shell. Make. Oh, right, I did not actually include PO42 words.h. Something very weird happened there. Oh, I see. It's it doesn't like the line which creates our set of words. It is unhappy with. All right. Well, we're not going to get back to that error message. Const std set. Oh, I didn't actually change this to set. Actually, I think what I'm going to do, no, I think this is fine. It's a little bit slow now that we have this giant pile of words up here, but I think this will be fine. Okay, let's run our solver. As you can see, it's going to take just a moment, but there we have it, our decrypted message. And you can see that it does appear as the #1 answer up here. From this point, to get the actual answer, we need to sum all the characters in the message to get our final answer. I'm not going to bother doing that now. We've already done that in the previous video. One interesting observation that I will make, though, is if we search for an extract taken from the introduction, something interesting happens. We see that the message we actually did find it yesterday. It's number 295. So our metric wasn't quite good enough for it to appear at the top of the list, or even in the top 100. But it was there. I probably even looked right over it at some point. But in any case, today we have a much better metric that went right to the correct answer. So I hope some of you found that enjoyable. And tomorrow we'll hopefully be looking at problem number 60. I'm warned that it's a little bit of a difficult problem, so that may not come out for a few more days. We shall see. In any case, I hope you'll look forward to that. Let's see. How is yesterday's video doing? Looks like we have a comment from a viewer. It says we just need to count the number of E's. Doesn't seem like that could be right. Son of